All right, in this example, we have a population mean and the standard deviation is unknown. So when we do not know the standard deviation of the population, we have to estimate it using the sample. When we do that, we can't use a z statistic anymore. We have to use a t statistic, so we have to use the t distribution. So the process is the same as what we did with the one sample z-test. But now with the one sample t-test, we just, I have to estimate our sample standard, or the population for the standard deviation of the population from the sample, and then we're also using the t-distribution instead of the standard normal. So let's look at the example, cost of residential water. So on its municipal website, the city of Tulsa states that the rate it charges per 5 CCF of residential water is $21.62. How do the residential water rates of other U.S. public utilities compare to Tulsa's rate? So we have a file with a bunch of data. It contains the rate per 5 cc of residential water for 42 randomly selected U.S. cities. So formulate the hypotheses to determine if, the charges differ from the rates, and then what is the p-value, what is our conclusion, and then also use the critical value approach. So everything that we've been doing before. So let's look at the data. So it is in Chapter 9 Practice, that Excel file under the Water tab. So here's all the different, the different municipalities or the different companies across the U.S., and here's their rates. So we want to calculate a sample statistic, a mean as a point estimate of the population, to compare to the mu of Tulsa, which is 2162. I have the solution there, obviously, but let's do this together. So we do have mu, the known population parameter that we're comparing it to, 2162. So we have to plug in the rest. So we need the average, from our sample. So that's just the equals average function. And then we have to, we don't know the population standard deviation, so we have to calculate it, So that's S. That's the standard deviation of the sample. So it's standard ST deviation, DEV dot S, for sample, that is the function to calculate the sample standard deviation. So we get 7.79. So we can kind of actually look at this to determine if this is probably significant or not, just by looking at the numbers. So our means, they're pretty close, It looks like on average it's a little over $1 less for everybody else compared to Tulsa. So it looks like it's cheaper, but look at the standard deviation. It's almost 7.8. So it's basically the standard deviation is $7.8. So that means that the standard deviation is, $7-8. So there seems to be a lot of variability given that we're dealing with a mean of 2021. So there's a lot of variability. So probably these differences, it's $1. So there is a difference. It seems to be $1 cheaper, but the standard deviation is high, so it probably isn't going to be significant. So sometimes you can just look at your data intuitively and think, does it make sense? Is this going to be significant or not, We do have a bit of a difference. It's about $1, but there's a lot of variability in the data, which kind of interferes with finding some type of significant effect. So anyways, let's keep going. Let's test it. The sample size is 42. That's given to us. Remember, we could also use the count function if we weren't given the sample size. So count A, that just counts all of the cells, a number of cells that have something in them. So that gives us 42 as well. Just remember, if you have missing data, so if Memphis here was just empty, that wouldn't be included, so that might affect your total sample size. So just be aware of little things like that. Okay, degrees of freedom. This is something new that we need that we didn't need with the one sample z-test. So the degrees of freedom is equal to our sample size minus 1. Our standard error, is the standard deviation divided by the square root of n. So that's our standard error. And now our t value, our t statistic, is going to be equal to x bar minus mu, the difference, right, divided by the standard deviation, right? The standard deviation of the sampling distribution is the standard error. So that's our t value. So again, typically t, when we approach about 2, somewhere around there, that becomes significant. So this actually isn't big. So again, this suggests that our results are not statistically significant. But let's keep going. Let's test it. So with the t-critical, this is the first approach, the critical value approach. We want to calculate a test statistic to compare to the test statistic that we calculated. So to do that, we can use the t, a couple different functions. We can do t dot inverse, right? So remember, if we use t dot, was it like t distribution, right? That's going to give us a probability, but we don't want a probability. So we know we have to use the inverse function. So this returns the left tail of the student distribution. So this is giving us the value to the left. So it takes a couple arguments, p. So we have to think about what to supply for the p-value, right? We know, I think we're working with 0.05, right? Alpha is 0.05. But remember, this is just asking if it differs. So we know this is a two-tailed test. So if it's a two-tailed test, right, we have to divide by our 0.05 divided by 2, which equals 0.025. So you can just plug in 0.025. And then ask for our degrees of freedom. So we have that. Let's just look again at the sheet that I gave you. So we're working with a t-test. We're trying to calculate our critical value. We know we're working with a two-tailed test, so we can actually use one of these two functions. So this is a little confusing because in one of them we're putting in 0.025 and the other is just 0.05. So that's a little bit confusing. The t dot inverse is a little bit more allows a little bit more flexibility. It's saying give us the p-value that we want. It's a little bit more specific. So we can do that. But the other one that we could calculate, right, there's a different option down here. There's no dot between t and inverse. So let's see what this one does. This one says it returns the two-tailed inverse, right? So this is actually saying that we're going to give you the two-tailed automatically. So for the probability, just tell us what alpha is, and we'll automatically give you a two-tailed test. So if you have a two-tailed test, you can just use the TINV function, and again supply the degrees of freedom, and look, you get the same answer. So again, this is our critical value. Remember, I told you it's somewhere around 2. So it's 2.102 if we're rounding. So remember, our t statistic has to exceed the critical value in order for us to reject the null, but it doesn't, as we suspected. So in this, we would know we fail to reject the null. So that's one approach. So we already kind of have our results that basically the prices do not differ from a statistical significance perspective. But we can continue with the p-value approach. So let's look at our handy-dandy chart. So we know that this is a two-tailed test. So we can use the t distribution function. So equals t dist, notice there's no dot in there, and this takes 3 arguments, x, so that's our t value right there, degrees of freedom, and tails. This one asks us, is it 1 or 2? It's 2. So the only thing with that is when we do this, we get a little error. So what we can do with this is actually for x, we're going to take the absolute value of our t value and then supply the rest of them. I wanted to point that out, that happens. And then we get an answer. So again, this value is not less than 0.05, so again we come to the same conclusion, fail to reject the null. And sometimes it's good to look at your t-value and your p-value because they do supply the same information. Like if we look at our t-value and our critical value, if we compare these two numbers, right, we're not even close to rejecting the null here. Like 1.18 or 1.4, right, or 1.5 if you're rounding, right, we're not even come close to to exceeding this critical value. Similar with our p-value, I mean, we're not even close to being less than 0.05. So the information should converge, right, when you're looking at the critical value approach and the p-value approach. So, so that's mostly it, I think, for the information that I asked for, right? What's the p-value? Can the null hypothesis be rejected? No. What's your conclusion, right, that they don't differ? Repeat this using the critical value approach. We did that. The only thing we didn't do is formulate our hypotheses. The most important thing, sorry, I skipped over it, right? The nulls, that there's no difference. So basically mu, right, they're the same as 21.62. The alternative is that they're not the same. So the exclamation point equals, that's our code, just means not equal. I think you can insert with symbols, by the way, if you wanted to. If you go up to insert, symbol, right, they do come up. There should be, yeah, there's a non-equal sign that you can just insert to be a little bit more correct. So that's the example for when we have a population mean with our standard deviation unknown for a two-tailed test.